Good afternoon. My name is V. Pradeep Reddy and I am from Aeronautical E section. And my high-speed aerodynamics topic is entropy change across a normal shock wave. Normal shock wave. As an object moves through a gas, the gas molecules are deflected around the object. If the speed of the object is much less than the speed of the sound of the gas, the density of the gas remains constant and the flow of gas can be described by conserving movement and energy. As the speed of the object increases towards the speed of sound, we must consider compressibility effect on the gas. The density of the gas varies locally as the gas is compressed by the object. For compressible flows with little or small flow turning, the flow process is reversible and the entropy is constant. The change in flow properties and then are given by the isentropic relations. Isentropic means constant entropy. But when an object moves faster than the speed of sound and there is an abrupt decrease in the flow area, the flow process is irreversible and the entropy increases. Shock waves are generated. Shock waves are very small regions in the gas where the gas properties change by a large amount. Across a shock wave, the static pressure, temperature, and gas density increases almost instantaneously because a shock wave does no work and there is no heat addition. Total enthalpy and the total temperature are constant, but because the flow is non-isentropic, the total pressure downstream of the shock is always less than the total pressure upstream of the shock. There is a loss of total pressure associated with the shock wave. The ratio of pressure is shown on the downslide. Because total pressure changes across the shock, we cannot use the usual form of Bernoulli's equation across the shock. The Mach number and speed of the flow also decrease across a normal shock wave. If the shock wave is perpendicular to the flow direction, it is called a normal shock. On this slide, we have listed the equations which describe the change in flow variables for flow across a normal shock wave. The equations presented here were derived by considering the conservation of mass, momentum, and energy. For a compressible gas, while ignoring viscous effects, the equations have been further specialized for a one-dimensional flow without heat addition. A normal shock occurs in front of a supersonic object if the flow is turned by a large amount and the shock cannot remain attached to the body. The detached shock occurs for both wedges and cones. A normal shock is also present in most supersonic inlets. Across the normal shock, the flow changes from supersonic to subsonic conditions since gas turbine engines operate under subsonic conditions. It is necessary to introduce a normal shock in the inlet compression system. Across the normal shock wave, the Mach number decreases to a value specified as m1. m1 power 2 equals to gamma minus 1, m power 2 plus 2, 2 power gamma into m power 2 minus gamma minus 1, where gamma is the ratio of specific heats and m is the upstream Mach number. The total temperature Tt across the shock is constant. Tt1 by Tt0 equals to 1. Entropy. Subsonic flow after shock, mx equals to 1. Supersonic flow before shock, mx. S5 minus S6. Zone 0 upstream, the change in entropy across the normal shock wave. Entropy change formula. The change in entropy can be determined by considering the difference in the initial and final state of a system. So, delta S equals to SF minus SI, where delta S denotes entropy change, SF denotes final state, SI denotes initial state. Entropy change expression. The general expression for the change in entropy is delta S equals to Q REF T. In the above equation, Q is the heat and T is the temperature. The ideal situation for the process is delta S total equals to delta S system plus delta S surroundings greater than 0 plus. This means that the change in entropy should be greater than 0. Thank you.